Okay, so this brings us to the second part of this whole conversation, in which we're going to talk about photoconductivity. So photoconductivity, intuitively, it's material that has an increased conductivity when irradiated. Now, a lot of the conversations that we had before was all about increasing it with temperature, making things jump the gap with temperature. But we know that temperature is something that contributes to an energy of the carriers, but also light can be equated to an energy. So as long as you're able to bridge this gap with something, that something can very well be temperature, but it could also be light. So, for instance, semiconductors like cadmium sulfide or cadmium selenides, since they have a band gap of 2.4 electron volt, it means that that exact bridge of energies can be overcome when you have a light that passes through of 520 nanometer. This is equivalent to having visible light in the green side. And if you change the band gap, you can see that the intensity of what you can pass through actually changes with the band gap energy. So you have a different color of this cadmium sulfide, cadmium selenide, cadmium sulfide selenide, because you're changing the band gap, and this will change how much energy is needed to bridge in the gap. So you can virtually span them through all of the visible range and something more. Silicon, when you look at it, is fundamentally black. So it's not colored. We don't expect it to absorb invisible light. The gap of undoped silicon is 1.1 electron volt, which means that the corresponding energy in wavelength it's 1100. 1100 is not invisible light, is in near infrared, so it will look like dark to you because it doesn't see colors, but you can bridge the gap with this near infrared light. So if you shine infrared light through that, this should increase the conductivity. Note that a lot of nice technological stuff like photocopying basically is based itself on the fact that you increase the conductivity and you create carriers if you pass light through something. So you know, when you activate a photocopy, you have this light that passes through first of all, and then it goes on the other side. This is exactly what are you trying to do there. But photocopying and xerography is mostly done with amorphous selenium. And this brings me to something that we can discuss later. What is like band gap in something amorphous? Do you foresee any issues in trying to figure out what is the band gap? But if you want to look up how photocopying is done, it's basically all used on this activation of how many carriers do you have and stuff like that. This is a bit of an old style photocopying, but it's still a good concept. Now, this brings us to a bit of a chicken and an egg situation. Like, you can immediately see sort of where we are going, because solar cells is something that we are all very familiar with, even more so as we're having a lot of conversations about how to have renewable energies and stuff like that. This could bring you to, is it the chicken or the egg that came first? Did they figure out the photoconductivity first, or did they figure out that they wanted to have solar cells first? It's a bit difficult to discern, because basically these photovoltaic and photoconductive effects were all discovered first in the 1800s, and the first description of the solar cells came right after the first discovery of, oh, if you can make a voltage, you can make it conductive. If you can make it conductive, can we actually make electricity with light? So the first gold-coated selenium solar cells was in the almost 1900 at a very, very low efficiency in comparison to what we are used at the moment. But it's not a super new technology. We had this idea a while ago. It was something that came upon very quickly as this whole electricity business actually was systematized in science. And use of photovoltaics from the first application in the 1950s, in which it was something relegated to only the space science and these very pioneered applications in which you needed something to make electricity at all costs, even with low efficiency, actually spread all over the place, and now we are used to see photovoltaic panels in houses, on roofs, and stuff like that. You go out, you see one, and you give it as a standing technology. So how does it actually work when you try to make something that will make you electricity based on the semiconductors? So as we were saying before, if you don't have anything acting on your p-n junction, the p-n junction reaches a point of equilibrium. The majority carriers and the minority carriers kind of cancel each other out. You have this band bending, nothing changes anymore, and you call it a day. What happens when you irradiate your junction? What happens upon irradiation is that you modify the equilibrium of your junction, because the light that you're shining upon it, just like temperature, is creating additional carriers. So by shining light upon it, there is a certain probability that you will take an electron from the valence band and push it all the way through the conduction band. Now this is particularly tricky when you have a p-n junction in between, because it means that you will form a pair, but this pair will feel the potential through the junction and will try to drift off. Now if you put your, depending on that trick that you do on your material, how much bias do you put when you actually connect the junction, you can make use of this creation of carriers in a different way. So when you put the reverse flow, you reduce the energy barrier in between. So by knowing that you're irradiating, you make a photocurrent that passes through until you bring everything in balance back. So this is called the photovoltaic mode, and it's sensitive. It's a way that also, if you want to detect light and something like that, is something that you will likely use. In the photoconductive mode, which is the one that you also see in the image, you apply an additional bias, and you make the step of the band bending increase. So what your electrons will see is this energy bridging given by your light plus the bias that you're putting, and you will separate off the carriers off as a DC current going through, because they see the very sharp step, so they want to get rid of this change of potential as soon as possible. So you can see that when you connect the bias, the photocurrent goes in this direction. So electrons on one side, holes in the other. Depending on where you apply the bias, you can make this thing go faster, slower, and stuff like that. So the photoconductive mode, if you're trying to really detect something very, very fast, so you know that there is something radiating, you want to get that signal immediately, it will be the fastest mode to measure something. It will be slightly more noisy, because of course you're creating something that really wants to equalize anything that passes through. So on top of your light, you will also collect other stuff. This response time is important when you're thinking about like junctions and photo junctions, so something that you want to use with light, because the response time is the thing that makes this thing functional. So how can you make sure that you have the fastest possible response to the lowest, teenier amount of light that you put on your material? Since we saw that to be able to have a response from your material, you need to apply something potential to your junction, and the junction has a band bending based on this depletion zone. The trick usually is to have layers that are different from just P and N. So for instance, something that works remarkably nice is something like a pin diode. So you have the N region, an intrinsic region in between, and a P region on the other side. If your dopant concentration is low enough on the two sides, and remember these things are small, what you create is a state in which the depletion zone will actually bring itself all the way up through the whole intrinsic semiconductors. So just span all the way up, and when you apply the bias all the way across, even if it's a tiny bias, the depletion zone will extend. So it means that you get a faster response because there is less, that you're making a trick with the amount of potential that you put in between. So this means that you give different energy states, and it's easier with lower amount of photons to actually get something out of it, because you increase the probability that you will manage to see carriers moving around with less noise. The other thing that you can do, which is a completely different business, so it's the opposite type of business, you basically make a huge dopant concentration in your materials. So you could have an incredibly p-doped part, an incredibly n-doped part, a normal p-type, and something more intrinsic. When you have this high dopant concentration, that puts a lot of carriers to begin with in the depletion zone, the drifting that you have when then you put the reverse bias basically causes an avalanche. So when you start to conduct, you conduct everything. So you create more and more and more carriers as your carriers move through. So you can see here, as you get the light in, you create the pair, but as the pair moves, because it feels the bias, it will start to activate the conduction of a series of other carriers. So what you will see at the end is much stronger than the effect that you created at the beginning. So this is what you detect on the other side, but this is what you created at the beginning. So the avalanche is something that you want, because either you want more carriers, you want this to go faster, you want to see it better. So this brings us to what you do with solar cells, which is exactly the same concept that we've been discussing through this whole thing. You conduct a P and an N junction, so you have this layering of your material. You want to connect them to something, because if you just keep them as they are, they will just recombine, have this depletion zone, nothing moves anymore in the depletion zone. But when you connect them to something and you expose the p-n junction to light, getting light in creates the pair. The pair splits, it feels the potential, and instead of waiting for this thing to recombine, due to the fact that you connected them to something, you make the electron feel the potential, the electron will move following the potential, and you will recombine just on the other side. So this is how you create electricity, but you can only do that depending on what bias do you apply, because you have that band bending option, and you have this tendency here in between to equalize and keep everything steady. Any change to the steadiness that is induced by something, in this case light, can be exploited if you manage to recover whatever gets created by the split and then re-equalize it with time on the other side. If you go to this link, you will see a nice animation of what happens when you actually hit a solar cells and this splitting of the charges and conducting through. So this is something that you're trying to move away from re-equalizing by itself. This concept is the concept that is applied to each and any solar cell, and this is what you have in the solar cells that you're more used to, which are the first and second generation solar cells. So you mostly do this, like all of these solar cells, you do them with silicon, so they're all silicon based-ish, and the original design is with a monocrystalline. So you do a single crystal of silicon, you do the doping, as we were discussing, you layer them up, and you make them act as your solar cells. So it works exactly like the design before, no changes, and everything you can consider it uniform because you're using a single crystal of solar cell. The thing that you want here is a band gap that responds nicely to light. The gallium arsenide is also another option, so instead of having silicon, you could use gallium arsenide. Why would you use gallium arsenide as a semiconductor? Fundamentally because it has a higher mobility of the electrons, so when you create a lot of the electrons, it's faster to move them around in the material. The band gap is slightly wider, so it helps doing this trick. And also you want to make sure that the heat doesn't create issues, because remember, these things get irradiated by light constantly. They heat up. Heating up a solar panel is never a good idea. You want to keep as low noise around as possible. Heating it up creates issues, but you cannot avoid heating it up because this thing is dark and is absorbing light, and there will always be some loss as the heat that goes around. Think of having a monocrystalline solar cells instead of other types is that it allows you to not recombine electron a hole as you are making the stuff go through, because the issue is that the more point of like ununiformity that you have in your material, the more likely it is that at some point the carrier that you just created by irradiating your solar panel with light will just get annihilated by something else and will not go on the other side. So the more electrons are actually able to go through your circuit and get fed into something else, the better served you are. If they block themselves through the path, you will lower the current. This is something that you cannot avoid in total, but if you can reduce it, it will be better. So these are pricey, inevitably, because they are from a single crystal of silicon. It's a more difficult thing to process, but they are more efficient per any area that you actually expose to light. If you want something cheaper, you can do this with polycrystalline silicon, and polycrystalline means that it's less precisely processed. So through this whole arrangement, you don't have a single crystal of silicon, you have several crystals of silicon, still with the same concept of doped and stuff like that. They are lower efficiency, but they are improving them with time and with tricks that we will see later. And still, they work nicely and they could be preferred because they are cheaper. So if your thing doesn't require a huge amount of electricity and you just want it to be solar power and you can live with lower cost for a lower efficiency as long as you can actually make it work, this is probably what you want. Even potentially lower efficiency, but with the power of being bendable, is the thin film solar cells. So you can actually put a photovoltaic material on glass. What material depends, so you can have silicon in amorphous form, it will work the same concept, or this series of cadmium telluride, copper indium gallium selenide, or the dye sensitized solar cells. These are the cheapest possible panels that you can have, and the fact that they are bendable and you can put them on glass makes them very, very, very attractive, They are considered to be the lowest efficiency among the solar panels that you can possibly have, but this thing has been on the rise quite a lot, so you can actually rely on them to be more behaving than just 10%, and they can really be used with a lot of applications. So it's cheaper, and it could be more attractive if you can have it cheaper and working and bending through different applications than just having a block of pricey monocrystallized single crystal silicon. Now, we've been talking about efficiency, how much energy you're able to convert and arrange and do. Can you have 100% efficiency of this thing? Would be ideal, but the answer is absolutely not. You cannot do 100% efficient solar cell conversion. So it doesn't matter how much effort do you put, you will never convert 100% of the light that you pour inside your material into electricity. This is just not possible. This is not a concept that is completely new, like in the same way you cannot have a combustion engine with 100% efficiency. This doesn't work. It's thermodynamics, hands us all. And the thermodynamic limit in this case also has an additional issue, which is you need to think about your material as something with potentially a single junction, so a single band gap. You have your PN junction. Your PN junction has one band gap, meaning that it cannot absorb through the whole spectrum to begin with. You have one band gap. The band gap is the energy at which this thing works. So you want to stay at a specific energy. You will have a series of losses. So a lot of the losses are connected to the fact that you have heat in your material. So not all the energy that you're putting in will be used to generate and conduct a pair of an electron and a hole. It might very well be used to generate heat and disperse heat through the material. You can try to reduce this, but it will be impossible to bring it to zero. And another issue that you might have in your material is the transmission losses, because we've been talking about you have the PN junction, but as we were saying before, you need to connect it to something, and you need to drag the electrons off to actually be used somewhere else. This point of mobility and conduction will reduce the amount of energy that you'll actually be able to carry through. Once you get rid of this very huge amount of contribution to your efficiency, you're left with this type of green bell that you see under here, and you can see that the bell, as a lot of these losses, actually changes with the energy of your material. So how big is your band gap? This changes how much are you actually able to convert in terms of photovoltaics. So a lot of the stuff that we are using sort of peaks at 33% maximum. Is not because we are not able to do this better or because we are not putting enough effort. It's because with a single possible junction, this is the peak efficiency. You can try to improve the arrangement, reduce some of the losses, cool down your panels and stuff like that, but given that you have a band gap, that will be your maximum efficiency. So you can see here that you have a series of possible materials and their relative band gap. So crystalline silicon, amorphous silicon, cadmium tellurite, indium phosphate, gallium arsenide. And this thing is what we call the limit of efficiency of a solar cell, known also as the Schock-Queisser limit. So you can see that you can try to push from this nice 20 all the way up, but there is a very sharp limit for which after that you won't be able to go higher. This is something that you need to consider. You need to be honest with yourself and know that there is a limit over which your solar cells is not going to be as efficient as you want it. And in the next part, we're going to discuss like how do we actually get to having these limits, so what are the possible contributions to this game that you have here, because we talk about quickly about some of these things, but we can actually visualize it better. And what do you do to push the limit? Because God forbid we don't try to push away from a limit of efficiency of something that we want to work better. So this will be the next and final part of the lecture about overcoming limitations and higher efficiency solar cells.